In mathematics, the differential geometry of surfaces deals with the differential geometry of smooth surfaces with various additional structures. Most often, a Riemannian metric. Surfaces have been extensively studied from various perspectives. Extrinsically, relating to their embedding in Euclidean space, and intrinsically, reflecting their properties determined solely by the distance within the surfaces measured along curves on this surface. One of the fundamental concepts investigated is the Gaussian curvature, first studied in depth by Carl Friedrich Gauss, who showed that curvature was an intrinsic property of a surface, independent of its isometric embedding in Euclidean space. Surfaces naturally arise as graphs of functions of a pair of variables, and sometimes appear in parametric form or as loci associated to space curves. An important role in their study has been played by Lie groups, namely the symmetry groups of the Euclidean plane, the sphere and the hyperbolic plane. These Lie groups can be used to describe surfaces of constant Gaussian curvature. They also provide an essential ingredient in the modern approach to intrinsic differential geometry through connections. On the other hand, extrinsic properties relying on an embedding of a surface in Euclidean space have also been extensively studied. This is well illustrated by the nonlinear Euler-Lagrange equations in the calculus of variations. Although Euler developed the one-variable equations to understand geodesics, defined independently of an embedding, one of Lagrange's main applications of the two-variable equations was to minimal surfaces, a concept that can only be defined in terms of an embedding. Overview. Polyhedra in the Euclidean space, such as the boundary of a cube, are among the first surfaces encountered in geometry. It is also possible to define smooth surfaces, in which each point has a neighborhood diffeomorphic to some open set in E2, the Euclidean plane. This elaboration allows calculus to be applied to surfaces to prove many results. Two smooth surfaces are diffeomorphic if and only if they are homeomorphic. It follows that closed surfaces are classified up to diffeomorphism by their Euler characteristic and orientability. Smooth surfaces equipped with Riemannian metrics are of foundational importance in differential geometry. A Riemannian metric endows a surface with notions of geodesic, distance, angle, and area. An important class of such surfaces are the developable surfaces. Surfaces that can be flattened to a plane without stretching. Examples include the cylinder and the cone. In addition, there are properties of surfaces which depend on an embedding of the surface into Euclidean space. These surfaces are the subject of extrinsic geometry. They include minimal surfaces as surfaces that minimize the surface area for given boundary conditions. Examples include soap films stretched across a wireframe, catenoids and helicoids. Ruled surfaces are surfaces that have at least one straight line running through every point. Examples include the cylinder and the hyperboloid of one sheet. Any n-dimensional complex manifold is, at the same time, a dimensional real manifold. Thus any complex one manifold is a smooth-oriented surface with an associated complex structure. Every closed surface admits complex structures. Any complex algebraic curve or real algebraic surface is also a smooth surface, possibly with singularities. Complex structures on a closed-oriented surface correspond to conformal equivalence classes of Riemannian metrics on the surface. One version of the uniformization theorem states that any Riemannian metric on an oriented, closed surface is conformally equivalent to an essentially unique metric of constant curvature. This provides a starting point for one of the approaches to Teichmuller theory, which provides a finer classification of Riemann surfaces than the topological one by Euler characteristic alone. The uniformization theorem states that every smooth Riemannian surface is conformally equivalent to a surface having constant curvature. and the constant may be taken to be 1, 0, or -1. A surface of constant curvature 1 is locally isometric to the sphere, which means that every point on the surface has an open neighborhood that is isometric to an open set on the unit sphere in E3 with its intrinsic Riemannian metric. Likewise, a surface of constant curvature 0 is locally isometric to the Euclidean plane, and a surface of constant curvature -1 is locally isometric to the hyperbolic plane. Constant curvature surfaces are the two-dimensional realization of what are known as space forms. These are often studied from the point of view of Felix Klein's Erlangen program, by means of smooth transformation groups. Any connected surface with a three-dimensional group of isometries is a surface of constant curvature. A complex surface is a complex two-manifold and thus a real four-manifold. It is not a surface in the sense of this article. Neither are algebraic curves or surfaces defined over fields other than the complex numbers. History of surfaces. Isolated properties of surfaces of revolution were known already to Archimedes. The development of calculus in the 17th century provided a more systematic way of proving them. Curvature of general surfaces was first studied by Euler. In 1760 he proved a formula for the curvature of a plane section of a surface, and in 1771 he considered surfaces represented in a parametric form. Monge laid down the foundations of the theory in his classical memoir L'application de l'analyse à la géométrie, which appeared in 1795. The defining contribution to the theory of surfaces was made by Gauss in two remarkable papers written in 1825 and 1827. This marked a new departure from tradition because for the first time Gauss considered the intrinsic geometry of a surface, the properties which are determined only by the geodesic distances between points on the surface independently of the particular way in which the surface is located in the ambient Euclidean space. The crowning result, the theorem or egregium of Gauss, established that the Gaussian curvature is an intrinsic invariant, i.e., invariant under local isometries. This point of view was extended to higher dimensional spaces by Riemann and led to what is known today as Riemannian geometry. The 19th century was the golden age for the theory of surfaces, from both the topological and the differential geometric point of view, with most leading geometers devoting themselves to their study. Darboux collected many results in his four-volume treatise Théorie des surfaces. The presentation below largely follows Gauss, but with important later contributions from other geometers. For a time Gauss was cartographer to George III of Great Britain and Hanover. This royal patronage could explain why these papers contain practical calculations of the curvature of the Earth based purely on measurements on the surface of the planet. Curvature of surfaces in E3. Informally, Gauss defined the curvature of a surface in terms of the curvatures of certain plane curves connected with the surface. He later found a series of equivalent definitions. One of the first was in terms of the area expanding properties of the Gauss map, a map from the surface to a two-dimensional sphere. However, before obtaining a more intrinsic definition in terms of the area and angles of small triangles, Gauss needed to make an in-depth investigation of the properties of geodesics on the surface, i.e., paths of shortest length between two fixed points on the surface. The Gaussian curvature at a point on an embedded smooth surface given locally by the equation Z equals F in E3 is defined to be the product of the principal curvatures at the point. The mean curvature is defined to be their average. The principal curvatures are the maximum and minimum curvatures of the plane curves obtained by intersecting the surface with planes normal to the tangent plane at the point. If the point is with tangent plane Z equals 0, then, after a rotation about the Z-axis setting the coefficient on xy to 0, F will have the Taylor series expansion. The principal curvatures are K1 and K2. In this case, the Gaussian curvature is given by and the mean curvature by. Since K and Km are invariant under isometries of E3, in general, and where the derivatives at the point are given by P equals Fx, Q equals Fy, R equals Fxx, S equals Fxy, and T equals Fyy. For every oriented embedded surface, the Gauss map is the map into the unit sphere, sending each point to the unit normal vector to the oriented tangent plane at the point. In coordinates, the map sends to direct computation shows that the Gaussian curvature is the Jacobian of the Gauss map. Examples: surfaces of revolution. A surface of revolution can be obtained by rotating a curve in the xz plane about the z-axis, assuming the curve does not intersect the z-axis. Suppose that the curve is given by width t lies in, and is parametrized by arc length, so that then the surface of revolution is a point set. The Gaussian curvature and mean curvature are given by geodesics on a surface of revolution, are governed by Clairaut's relation. Quadric surfaces. Consider the quadric surface defined by this surface admits a parametrization. The Gaussian curvature and mean curvature are given by ruled surfaces. A ruled surface is one which can be generated by the motion of a straight line in E3. Choosing a directrix on the surface, i.e., a smooth unit speed curve C orthogonal to the straight lines, and then choosing U to be unit vectors along the curve in the direction of the lines. The velocity vector v equals quantum u satisfy the surface consists of points as S and T vary. Then, if the Gaussian and mean curvature are given by the Gaussian curvature of the ruled surface vanishes if and only if at and v are proportional. This condition is equivalent to the surface being the envelope of the planes along the curve containing the tangent vector v and the orthogonal vector u, i.e., to the surface being developable along the curve. More generally, a surface in E3 has vanishing Gaussian curvature near a point if and only if it is developable near that point. Minimal surfaces. In 1760, Lagrange extended Euler's results on the calculus of variations involving integrals in one variable to two variables. He had in mind the following problem. Given a closed curve in E3, find a surface having the curve as boundary with minimal area. Such a surface is called a minimal surface. In 1776, Jean-Baptiste Meusnier showed that the differential equation derived by Lagrange was equivalent to the vanishing of the mean curvature of the surface. A surface is minimal if and only if its mean curvature vanishes. Minimal surfaces have a simple interpretation in real life. They are the shape a soap film will assume if a wireframe shaped like the curve is dipped into a soap solution and then carefully lifted out. The question as to whether a minimal surface with given boundary exists is called Plateau's problem, after the Belgian physicist Joseph Plateau, who carried out experiments on soap films in the mid-19th century. In 1930, Jesse Douglas and T. Barrado gave an affirmative answer to Plateau's problem. Many explicit examples of minimal surface are known explicitly, such as the catenoid, the helicoid, the Shirk surface and the Eniper surface. There has been extensive research in this area, summarized in Osserman. In particular, a result of Osserman shows that if a minimal surface is non-planar, then its image under the Gauss map is dense in S2. Surfaces of constant Gaussian curvature. If a surface has constant Gaussian curvature, it is called a surface of constant curvature. The unit sphere in E3 has constant Gaussian curvature +1. The Euclidean plane and the cylinder both have constant Gaussian curvature 0. The surfaces of revolution with phi tt equals phi have constant Gaussian curvature -1. Particular cases are obtained by taking phi equals c cosh t, c sin t and ca. The latter case is the classical pseudosphere generated by rotating a tractrix around a central axis. In 1868, Beltrami showed that the geometry of the pseudosphere was directly related to that of the hyperbolic plane, discovered independently by Lobachevsky and Beaulier. Already in 1840, Minding, a student of Gauss, had obtained trigonometric formulas for the pseudosphere identical to those for the hyperbolic plane. This surface of constant curvature is now better understood in terms of the Poincare metric on the upper half-plane or the unit disk, and has been described by other models such as the Klein model or the hyperboloid model, obtained by considering the two-sheeted hyperboloid Q equals -1 in three-dimensional Minkowski space, where Q equals x2 plus y2 z2. Each of these surfaces of constant curvature has a transitive Lie group of symmetries. This group theoretic fact has far-reaching consequences, all the more remarkable because of the central role these special surfaces play in the geometry of surfaces, due to Poincaré's uniformization theorem. Other examples of surfaces with Gaussian curvature 0 include cones, tangent developables, and more generally any developable surface.